In this presentation, I want to discuss some of the work I've been doing, I did during my PhD, and some of the work I've been doing during my postdoc at Johns Hopkins. But before I start, I want to acknowledge some of the people who worked with me on the projects I'm going to show today. So in Lausanne, I was supervised by Professor Jean-François Molinari and Guillaume Anciot. And I've worked with Marc Bonnet on some of the mathematical aspects of what I'm going to present today. And in Baltimore, I was working with Professor Mark Robbins until he unfortunately passed away last summer. And since then, I've been working with Professors Jafar Al-Awadi and Vicky Nguyen on, in particular, a project that also involves an experimental group in Central Lyon that is led by Juliette Caille-Barrios. So as a researcher, I'm interested in solid interfaces and what happens when two solids slide on top of each other. You might know that you have energy dissipation due to heat. You might also have damage at the contact interface, and this damage can lead to the formation of third-body debris particles that leads to wear of materials. One of the reasons we're interested in this problem is because together friction and wear account for 26% of the world energy consumption, and since we still rely heavily on fossil fuels to generate energy, these turn out to be large amounts of CO2 emissions. So friction and wear are phenomena that occur virtually on every scale or every length scale. We can have friction for earthquakes, for example, at the kilometer scale. We can have friction at the nanoscale. And in some cases, for friction, we want to maximize the amount of energy dissipated. Sometimes we want to minimize it. And for wear, wear is basically inevitable, but it dictates the lifetime of our engineering systems, for example, bridge bearings here. So to harness those two phenomena, we need to have good predictive models to be able to design efficient systems. However, there are no predictive models for either friction or wear. Here you have I selected two rather simple models for friction and wear. You have the familiar Amont-Coulomb friction law with the friction coefficient, and simple wear law, which is the Archard wear law, which states, if you're not familiar with it, that the wear volume is proportional to the normal force times the sliding distance divided by the hardness of the materials in contact. What both of those models have in common is that they need a coefficient here, K is called the wear coefficient, and mu is the friction coefficient. Those coefficients need to be informed with experimental measures. And therefore, those models are not predictive. What they also have in common is a linear dependency on the normal force and an absence of dependency on the apparent contact area. Here, in both of those equations, the size of the contact, the apparent contact, does not play a role. We've known this for a few centuries now, because Da Vinci actually did experiments on this, where he was measuring the static friction force for different orientations of a single block, and he found that the orientation of the block had no bearing on the static friction force. Now, the reason this is the case is due to inevitable roughness that occurs at the interface. And roughness is a fundamental aspect of tribology, and it governs a lot of what we observe at the macro scale for friction and wear. And so we need to be able to describe properties of roughness. And you might know that roughness has a self-affine characteristic in natural surfaces. So this work here by François Renard and co-workers, they've done measurements of geological fault surfaces at the kilometer scale, at the meter scale, at the centimeter scale. And what they found was that there, as you zoom in scales, you still find more and more roughness. What they also did was to compile power spectral density for those first roughness measurements. And they put it here in this plot where they have measurements of different roughnesses at different scales. And they have a nice parallel scaling over tens of orders of magnitude, which means that roughness is basically a scale-free occurrence in nature. There isn't a particular scale that determines the roughness of a surface. So since roughness is so important to friction and wear, you might think that since it's scale-free as well, friction and wear might also be scale-free phenomena. However, this isn't the case. To illustrate this point for wear, I chose this work of Kandela and Brodsky, where they did measurements of roughness of a geological fault. Here you see on this picture and here on this topography map, there is anisotropy because the fault before being exposed used to be sliding. And so you can clearly see the sliding direction in the anisotropic roughness. But if you zoom in and you look at the roughness at the micro scale, the anisotropy disappears and you have isotropic roughness. So there's clearly a physical phenomenon here that's at play with a characteristic scale that distinguishes between microscale here and meter scale in this case. There are also characteristic length scales for friction. These are some of the experimental results I will discuss a bit today from LTDS Central Lyon. I will discuss them further, but basically for now, what you need to know is that it's a sliding experiment where the velocity is adjusted during the sliding process. They measure the friction force, and what they have when they change the velocity is an overshoot in the friction force, which decays towards a new steady state value. And this decay occurs over a characteristic scale d0. So what I want to discuss today are two approaches, which I think are complementary and necessary to be able to model friction and wear. There's the continuum side of things, which I focused on during my PhD, which I think is necessary to be able to bring some of the mechanisms we know from the nanoscale up to engineering scales. And to do this, we need to account for the full breadth of roughness of natural surfaces. And what I've been doing during my postdoc is focused more on atomistic modeling, exploring the physics of nanoscale friction and wear. And those can be used to inform the continuum scale models that are going to be used to homogenize and scale up to engineering scales. So the presentation is going to be split into 3 parts. The first 2 will deal with continuum modeling of rough contact interfaces. We'll talk about this in the first part, and in the second part, we will talk about plasticity and its influence on crack nucleation at contact interfaces. And the last part will deal with molecular modeling, and we'll discuss aging friction at the nanoscale. So let's start with rough contact modeling. This is a picture, an experimental picture of a rough contact interface. The colored spots you see here are the micro contacts. This is where you actually have the solids that are touching. And it's very important to be able to model these contact spots as accurately as possible, because this is where there is interactions between 2 bodies that slide or wear. So you might think that since the true contact area, the area where forces are transmitted, is so small compared to the apparent contact area, the local pressures must be really high. And they are actually high enough that they cause irreversible damage or irreversible deformations in the bodies in contact. And we've known this for a while, but I find those experiments by Daniel Bonn and his team to be really visual to show this. This is the experimental true contact area for a rough sphere on top of a flat surface. And this is a corresponding simulation that uses the true roughness measured in the experiment, but assumes elastic deformation. And you can see that it completely misses the mark on the true contact interface. So to be able to represent as accurately as possible the contact interface, we need to have a model and the corresponding numerical methods to be able to solve the contact problem, to have plasticity. And there are methods that do both. There are various finite element contact schemes that can handle both of those. But we also have an additional constraint, which is to account for the multi-scale aspect of roughness. And this usually means that we have to discretize our contact interface very finely, because we want to represent all of the details of the true contact interface. And there are methods that do roughness and contact, but that don't do plasticity. And those boundary integral methods are very interesting. And I will go into them a bit later, but we want to be really at the center of this Venn diagram here and do all 3 things at once. So some people have done that with finite elements, namely Mark Robbins and Jean-François Molinari. However, there are some shortcomings to using finite elements. One of them is that in order to avoid any effect of boundary conditions on the contact interface, you need to discretize a volume that is larger than the volume of interest where you expect to have plastic deformations. You can alleviate some of the computational burden by using a dynamic relaxation scheme, but for plasticity, this may not be an appropriate way to model plasticity because it's path dependent. So there are some issues with finite elements, and ideally we would try to solve those issues by having a numerical method which would allow us to discretize as finely as we can the contact interface, to discretize a part of the volume where we have plastic deformations, where we expect to have plastic deformations. And anything else outside of this would be taken care of because it's elastic and we wouldn't need to actually explicitly discretize it. So I've talked about methods that work really well for elastic contact with multiscale roughness, and those are boundary integral methods. And they revolve around the principle that you can express equilibrium surface displacements as a function of contact pressures using this convolution integral here. And the kernel you use for this convolution integral is the displacement that is due to a point force acting on a half space that is elastic. So if you can write your equilibrium using this equation, you can also write your potential energy, and elastic contact basically becomes a minimum principle of minimum potential energy under the constraint that the separation of the two surfaces should be greater than or equal to 0. Now, the main computational burden of this kind of method is to compute this convolution integral efficiently. And one of the best ways to do that is to go to the Fourier domain to be able to compute it. Historically, that's what people have done. And what they've done is to use a contact solution from the 1940s, early 1940s, which is the solution of a sinusoidal rigid surface on top of an elastic half space. And so the contact solution is very interesting because as you push the contact until you have no surface separation, you have a correspondence between your displacement and the sinusoidal contact pressures. So you have a proportionality between the two. And this coefficient here can be generalized to 2D if you have a 2D surface. And you can very well imagine how this can be efficient in the computation of a convolution integral, because using methods such as the fast Fourier transform, you can decompose contact pressure into a set of modes, apply this coefficient to each mode, and then recompose your equilibrium surface displacements using the inverse Fourier transform. So those are, in a sense, FFT-based boundary integral methods. They're very nice for elastic contact because they're really efficient. They focus all of the computational resources on the interface. We don't discretize anything inside the volume of the bodies in contact. They're really fast because of the fast Fourier transform, and they're rather easy to implement because fast Fourier transform libraries are readily available. So when I set out for my PhD, my initial goal was to try to retain those features to do elastoplastic contact. So one way I could have gone, and something that people actually do in the literature, is to leverage the principle of hardness. Basically, if you have an indenter that you push onto an elastoplastic solid, and you increase the load, if you measure the mean pressure at the contact, this pressure increases and saturates at a level here for a spherical indenter that's about 3 times the yield stress. So you could use this physical principle to modify your elastic contact problem and say that you want to minimize the potential energy under the separation constraint and an additional constraint which states that the contact pressures should be always smaller than the hardness of the material. However, this is a rather ad hoc way of doing plasticity in contact, and it's legitimate to ask the question, does it represent the right physics? So I didn't go this route during my PhD. What I did was to devise a method that is based on volume integral representations. So I have a half space with contact tractions and a distribution of plastic deformations. And what I want to do is to express my equilibrium displacements as a function of those two quantities. So for the contact tractions, I have this boundary term here, which is very similar to what I just showed before with boundary integral methods. And I have an additional term that takes care of the plastic deformation. And this expression here, I can only write if I choose wisely the Green's function here, G. This is just a shorthand for later on for the presentation. So I need to choose a Green's function that is appropriate so I can write this equation. Typically in integral methods, people use the Kelvin fundamental solution as a Green's function. And the Kelvin fundamental solution is a point force that is acting inside an infinite elastic medium. However, I cannot use this Green's function to write the previous equation. I need to use a different Green's function, which is the Midlin fundamental solution, which is the same thing. It's a point force acting in an infinite medium. But this time, this infinite medium is only infinite in two directions, and it's basically a half space. There's an additional constraint is that the surface, this boundary here should be a free surface. So the tractions of this solution, the surface traction should be equal to 0. This is what allows me to write the integral I showed in the previous slide. So in order to compute equilibrium displacements, there's this boundary integral term, which is being taken care of by the same methods that I showed before with the FFT. And there's this volume integral term. And I need to be able to compute this term as efficiently as possible. There is, in my problem, a translational invariance in two directions, in y1 and y2 directions, which means I could use 2D FFTs to accelerate the computation of this integral. However, when I started my PhD, the Midlin solution that I have to use here, this G, was only known in the physical domain. So I would have to either compute the convolution in the physical space using a different acceleration scheme than the FFT, such as a fast multiple method, but that would defeat the easy to implement condition that I took. I could also use a discrete Fourier transform of this Midlin solution, but that would introduce a sampling error because I need to sample the analytical solution, and I need also to store all the Fourier coefficients, which takes up a lot of space in memory. So what I did during my PhD was to derive the Midlin solution in a partial Fourier domain. Basically, I did a Fourier transform in the y1 and y2 directions, and I solved equilibrium for the Midlin solution directly in this hybrid system of coordinates. And that allows me to cancel any sampling error I would have if I had to do the discrete Fourier transform of the physical space solution. And also I have reduced memory cost because I don't need to store any of the Fourier coefficients. I have the analytical solution, I can compute them on the fly. For time reasons, I'm not going to go into the details of how I derived this fundamental solution. You can feel free to ask questions about it at the end, or to check out this notebook that contains all of the details and source code that derives this. So again, our goal is to compute this integral as efficiently as possible. I've shown that we can, thanks to translational invariance, we can compute part of this integral in the Fourier domain, but there's still a direction where we don't have translational invariance, that's the y3 direction. So we still need to integrate over y3. And naively, if you look at this expression here, for each value of x3 where you're interested in computing the displacement, you need to integrate over all the values of y3. And so if you discretize, that would mean you would get a quadratic complexity on the number of points you have in the depth. However, thanks to my knowledge of the analytical solution of G, I can use some clever mathematical tricks to accelerate this computation. And finally, I can recover the n log n complexity, which was my target from the start. Again, feel free to ask any questions about the details of this, or check out this publication if you want. So I can now compute efficiently equilibrium solutions if I have a set of contact tractions and a set of plastic deformations. So both of those are unknowns, and I will discuss now how we find plastic deformations. what we do is we write this same equation, we differentiate on each side to write the deformation instead of displacements, and we write it in incremental form. So this is basically giving the same information. I have the increment of total deformation as a function of the increment of contact tractions and the increment of plastic deformations. And here, you feel free to plug in any continuum plasticity formulation. If you take something like a radial return from Mrs. plasticity, the increment of plastic deformation is something that depends on the increment of total deformation. So you have a nonlinear implicit equation, which can be solved if you recast the problem into a root finding problem and solve with your favorite kind of nonlinear solver. They do need to be matrix free though, because we don't want to assemble tangents for this function, because those operators are full, and it would defeat the purpose of having worked all this way to have an n log n scaling of computation of equilibrium solutions. Finally, if we put everything together, there's two parts in the elastoplastic contact algorithm. There's a contact part, which is basically elastic contact. It assumes that the plastic deformations are constant, and it iterates to find new contact tractions. When we converge here, we can send our updated contact pressure to the plasticity problem, which is this root finding problem. Once we've converged for this, we have new plastic deformations which inform our contact problem, and we go on and on like this until we've reached convergence. So that's the end of the technical part. This is one of the results that we can get from such a simulation. These are the plastic zones. So those are all the zones where we have plastic deformation in a rough surface contact. The color here indicates the depth. So you can see most of those plastic zones actually located close to the surface. And this simulation was done with a code I wrote in C++, which is parallel and high performance. It's called TAMAS, and it's completely open source. Feel free to check it out if you want. So I've showed you a way to do elastoplastic rough contact, and I'm going to try now to apply it to a practical problem of wear modeling and the influence of plasticity on crack nucleation. So let's discuss a bit wear modeling. There have been some studies in the past 5 years, particularly in Jean-François Molinari's group, on microscale or nanoscale mechanisms of adhesive wear. If you're not familiar with this, or if you missed Jean-François's seminar a few months ago, just to recap a bit, there's a critical length scale to nanoscale wear. Basically, if you have two asperities that collide, and the contact is smaller than a critical length scale, you have plastic deformation, and you have no detachment of debris particles. So essentially, you have no wear. If the contact is larger than a critical size, then the adhesive forces that occur at the interface are strong enough so that you can have cracks that propagate in the bulk and detach the asperities. And what you also have is that if you have asperities that are close enough together, those couple of asperities are close enough together, you can have crack shielding mechanisms that kick in and allow only a single crack to propagate and detach a single wear debris particle. Essentially, what those studies have shown is that adhesive wear is a fracture process. So if you have enough elastic energy that is stored in your contact to form new crack surfaces, then you're going to have this brittle mechanism which leads to detachment of a debris particle. And if you don't have enough energy, then you have plastic deformation and the asperities just pass each other and there's no detachment of debris particles. But that's not the full picture, because if you want to model such a phenomenon on the scale of a rough surface with many rough contacts, you need to do crack nucleation. So either by defect or stress concentration, or if you have a cohesive zone modeling, for example, you could use critical nucleation stress or other kinds of models which include crack nucleation. And you need to have crack propagation with the energy dissipation, which I just showed, and interaction via bulk forces. So this is something that can be done with molecular dynamics. It's very natural in MD to do it. And you have here the interaction between two cracks, which leads to the detachment of a single debris particle. You can also do it at the continuum scale. This is work actually by Stella and Jean-François, where they used gradient-based damage models. And you see the same thing here of a single crack that propagates due to the elastic interactions between the two asperity contacts. However, with the methods I've showed you earlier in this presentation, I can only do elastoplastic contact. I cannot do crack propagation yet. That's something I'm interested in, but cannot do currently. So because I have a homogeneous flat half space, I don't also have defect or stress concentrations. And so I'm going to focus on having a crack nucleation stress. So the question I want to try to answer is, how do I quantify the probability that a microcontact in a rough contact interface with many, many microcontacts, how do I quantify this probability that a given microcontact will have a crack in its vicinity? And in particular, I want to understand what is the effect of plasticity on this probability. To do this, I did a set of rough surface contact simulations, where on each simulation, I look at the principal tensile stress at the surface. And I look at zones where the principal tensile stress is larger than the critical stress for crack nucleation. I did two sets of simulations. I did a set of simulations with a full description of plasticity, with von Mises plasticity in this case, using the method I described to you. And I did also a set of simulation using this elastic contact with added hardness condition. This is what I call saturated plasticity. And you can already see in black here, you have the zones where this condition is satisfied. So those are the crack nucleation sites. And hopefully with the video compression, I'm not sure it shows up, but you have some black pixels here on the left. But on the right, you have many, many more crack nucleation sites with a full description of plasticity. Whereas those are the same normal loads and the same yield stress. In red, you also have the plastic zones, which actually reach the surface in this case. So what I do to compute this probability that a contact will nucleate a crack is I count how many crack nucleation sites I have in my total system, and I divide it by the true contact area. This quantity turns out to be proportional to the probability of forming a crack. So this is what I show in this plot. This is the crack nucleation likelihood. This is the critical stress, and here is the normal load, which varies the colors here. So basically each curve corresponds to a different normal load. What's interesting is that if we look in this part of the graph, let's say we take sigma c to be 0.1 here, we have a much larger likelihood of nucleating cracks than in the case where we have full description of plastic deformations, than in the case where we just say that the pressure should saturate at the hardness. And this is interesting because this saturated model essentially deforms elastically. This is a purely elastic deformation mode, and we assume there's a crack that is inserted at a given stress. So this is essentially a brittle material. Whereas the J2 case here, the von Mises plasticity case, has a phase of plastic deformation, and so it's a ductile material. And it's interesting to note, and it's a bit counterintuitive, that the ductile material has a higher chance of nucleating cracks than the brittle material. I also did simulations where I do a normal loading, and I apply a shear stress to simulate the onset of sliding. And what I see in this case is that in the saturated case, where again, deformation is basically elastic, I have an increase, as I increase the load, I have an increase in my crack nucleation likelihood because the tensile stresses in the system increase. But in the case of having a full description of plasticity, I don't have this increase of the crack nucleation likelihood. So the probability is basically unaffected by the application of a shear stress in this case. To rationalize a bit those observations, I did simulations of a single asperity where I push a spherical indenter onto an elastoplastic half space. I shear it with tau j, and I compute the principal tensile stresses at the surface. And what I get is this curve of sigma 1 as a function of tau j. In blue, you have the elastic behavior, which is essentially unbounded. And as you increase tau j, you increase in proportion sigma 1. But if you have plasticity, you have something that is very similar to hardness. As you increase tau j, at some point, you deviate from the linear behavior, and you have a nonlinear state, where as you increase tau j, you don't increase as much the tensile stresses in the system. And this is apparent here in the softer case, where the yield stress is the lowest. You almost have a constant behavior, kind of like what you have in hardness in indentation. So this explains why there is no real dependency on tau j for the case where we have full plastic deformations. But there's also something that's interesting to note is this initial point here. So this is when tau j is equal to 0. This is pure normal contact. As we get softer and softer, as we decrease the yield stress, we have higher tensile stresses in the system. And this explains why we had a higher crack nucleation likelihood in the case where we had a full description of plasticity, because plastic deformations introduce tensile stresses. And when those plastic deformations reach the surface, the effect of those additional tensile stresses is the largest. And so, this is, we have subsurface plasticity that introduces tensile stresses and increases the crack nucleation likelihood. And again, we see the saturation effect of sigma 1 due to plasticity, and this is why we don't see as much of an effect when we have shear stresses. So what I want you to take away from this is that a more ductile material, a softer material, is more likely to crack due to subsurface plasticity. This isn't something that's been directly observed in experiments, but this is something we expect from Achard's wear law. We expect to have less wear volume, more wear volume as we decrease the hardness, as we get softer and softer materials. So that's the end of the continuum part. I've showed you what I think is an efficient method for rough surface elastoplastic contact, and I've applied this method to trying to compute a macroscopic quantity, this crack nucleation likelihood, on a rough surface interface for adhesive wear. Now, when I started my postdoc, I wanted to improve my knowledge of what happens at the nanoscale of the physical phenomena that actually give rise to the macroscopic picture that we see. And I was fortunate to work on a very interesting project that deals with fatty acid coatings and their frictional properties. So those coatings, generally in solution, can be used to decrease the friction coefficient at the sliding interface. So what you typically do is you have a solution of a fatty acid such as this molecule, you spread it across your surface, and what happens is that this hydrophilic group tends to bind to the surface. And the molecules self-assemble into a monolayer. There's typically only one molecule thickness on top of the surface where the molecules bind. And the interaction between the tails of those molecules is what gives the decrease of the friction coefficient. Those are interesting systems because fatty acids are commonly occurring compounds in nature, and therefore they have a rather small impact on the environment. And they're also interesting because we don't know everything about them. We don't know everything there is to know about their friction properties. So there are things we need to discover, and they can also inform some more generic models for friction. So those are the reasons that the LTDS in Central Lyon, led by Juliette Caillé-Barrios, have done experiments of those fatty acid coatings. So what they have is a glass sphere that sits on top of a flat surface. They have a solution at the interface. They control the sliding velocity and they measure the friction force. One of the things they observe, which I think is really interesting, is an aging phenomena. What they do in the experiments is that they slide, they measure friction force, they stop sliding and they measure the force that relaxes to a non-zero value. And when they reslide, when they start sliding again, what they observe is an overshoot in the friction force. And this overshoot decays as a function of sliding distance over a distance that they measure is about 5 nanometers. What they also measure is the increase in this friction force, the magnitude of the overshoot. And what they observe, they measure this magnitude as a function of waiting time, sorry. And what they measure, what they observe is a logarithmic aging of this overshoot in the friction force as a function of waiting time, 4 times that are above 2 seconds. For anything less than 2 seconds, they don't observe any overshoot in the friction force. So for those of you who are familiar with wet and stick friction, this might ring some bells. If you're not familiar with wet and stick friction, it's basically a class of models that are a bit more generic than the Coulomb friction law, in that they include dependency on sliding rate and time as the state. And they were initially developed for rock mechanics, for rock friction. I'm not putting all of the equations here. What you need to know basically is that there's a dependency of the friction coefficient on the logarithmic of a variable phi, which is called the state variable. And the state variable evolves with the following equation, which includes the sliding velocity and a characteristic distance, which is d0 called the rejuvenation distance. So now when I started working on this, I asked myself what would be here d0 in the case of where we have those fatty acid coatings. And if we have roughness at the surface, typically d0 is interpreted as the distance you need to slide in order to renew your microcontact population. So if you have 2 rough surfaces that slide on top of the other, you have an evolution of the contact population, which you see here in this video. And d0 would be the sliding distance you need to lose memory of your previous contact interface to renew your contact population. So what I did was to take the AFM roughness measurements from the experiments that were given to me by Juliette and do elastic contact simulations of 2 sliding surfaces. And what I measure is the survival contact fraction. So the amount of contact area, the fraction of contact area at a given sliding distance that is common with the initial contact area. And this survival contact fraction decays as a function of sliding distance until it reaches a steady state, where basically all of the memory of the initial contact area is lost. And this decay occurs in my simulations over a distance of 40 nanometers. So those simulations are purely elastic contact simulations that do not include those fatty acid molecules. And it's therefore apparent that roughness alone is not sufficient to explain what they observe in the experiment with this d0 of 5 nanometers, because we are an order of magnitude larger. So in order to get as close to the experiment as possible, I set up a molecular model for the fatty acid molecules that they use in the experiments. What I did was to use coarse-grained potentials, which allow me to save a bit on computational power, because I have each bead here is 2 CH2 groups. I set up a surface of those fatty acid molecules for the top and bottom surfaces, because we know that the friction interaction is going to emerge from the interaction between the tails of those molecules. I press with a normal force on this system, and I pull with a spring at a given velocity. Now, of course, I need to have roughness in the system, and I used directly the roughness data that was given to me from the experiments. I used it to generate periodic surfaces, and I included this roughness into my molecular model. So at the end, I have a model that is about 200 nanometers by 200 nanometers, and I can compute my friction force. So what I do is essentially the same protocol as in the experiment. I have an initial sliding phase So there's some noise here. This is inherently due to the roughness of the surface. So I have this initial sliding phase. That's the black curve. At some point of this sliding phase, I stop pulling on the spring, and then I let the system relax, and I have a relaxation in the tangential force. And I can see that I relax towards a value that is non-zero, just like in the experiments. And during this simulation, I restart the sliding process at different waiting times. Those are those colored curves here. And what I do is I look at specifically the transient regime, what happens really at the peak here. You can already see that there's a bit of an increase in the peak, but this is more apparent in this figure, where I plot everything as a function of sliding distance. And you can see in black, you have the steady state curve, which has no interruption in the sliding process. In blue is a rather low waiting time, and then you increase the waiting time. So you have this increase in the overshoot of the friction force. And this overshoot is a transient that decays and reaches the steady state again after a sliding distance that's about 5 nanometers. So those are like 51, 52 angstroms. So this is something very encouraging that corresponds to the experimental measurements. And what I also measure from those simulations is the magnitude of the increase of the overshoot. And I also see, just like in the experiment, a logarithmic aging in the friction force. So this is still work in progress. And as you can see, the waiting times here are in the scale of nanoseconds because I'm using molecular dynamics. Time scales of seconds are unfortunately not currently possible. So this isn't a full story, but I think it's a very nice springboard towards understanding the nanoscale mechanisms of those fatty acid, nanoscale friction mechanisms of those fatty acid molecules. So hopefully this convinces you that atomistic modeling is very relevant for tribology. So to conclude this presentation, I've showed two different aspects of tribology. One aspect at the continuum scale, where I discussed numerical methods for elastoplastic rough contact and the increase of probability due to plasticity of nucleating cracks at rough contact interfaces. And I also discussed to you the importance of atomistic modeling to be able to reproduce features that are observed in experiments and to try to uncover the fundamental friction mechanisms at the molecular scale. And there's still a lot to do, but that's it for my presentation today. And with this, thank you for your attention, and I'm happy to take any questions.